we begin with the last part of slide that was supposed to be delivered in the morning session. Now we begin with the inverse function and then logarithmic function and inverse trigonometric functions. And then we jump to limits of a function. So again, the material in this part up to part 4 is still some kind of rehearsal from your high school mathematics. So I believe I can go a little bit fast. Okay, inverse function. So in the morning we have learned about one-to-one function. Now we can use that one-to-one function as to learn about inverse function. So basically, if f is a one-to-one function on a domain D with range R, then we will have the inverse function f inverse or f power minus 1. Well, this is the symbol of inverse. And the inverse function is defined by this equation. So f inverse of B is equal to A if f of A is equal to B. And in this case, the domain and the range are flipped. So the domain of the function f becomes the range of the inverse function, and the range of the function f becomes the domain of the inverse function. That is precisely why we need f to be a one-to-one function to be invertible. So if f is not a one-to-one function, we cannot inverse it. We cannot invert it. So let me ask you a question. Do you remember what is the inverse of a sine function from your high school? What is the inverse of sine?
I forget, sir.
Okay. Let's say we have f of x equals sine x. Then the inverse is, you can write it as sine minus 1 x or arcsine of x. Do you remember it now? Okay. Now, in that case, now believe me that this is true. But from this morning, we know that sine of x is not a one-to-one function over for all x, right? So we have to restrict this sine x to, for example, we restrict the domain to be from minus pi over 2 until pi over 2. If we restrict the function this way, then we can have inverse like this. If we do not restrict the domain like this, the function sine x is not one-to-one. So in that case, the function does not have an inverse. But if you restrict the domain to minus pi over 2 up to pi over 2, the function does have an inverse. That is basically the idea of the inverse function. And here is the simple example. Suppose that we have a one-to-one function y equals fx given by this table. So we see that for each x, we have different corresponding f of x, right? In this case, this function x y equals to f of x is a one-to-one function, and then we can have the inverse to be like this: x equals to f inverse of y. How to get the inverse function? We simply flip the position. Now the top one is y and the bottom one is f inverse of y. So we simply need to flip it if we have this kind of table. But what if we have a function, defined function that is defined formally, not like this, not in this kind of table. So let's say we have the function y equals half of x plus 1. We are asked to find the inverse of this function, and we are asked to express the inverse as a function of x. So in this case, how to get the inverse? We simply need to solve this function for the variable x in terms of y. Now, to find, so this function, in this function, we have x as the independent variable and y as the dependent variable, because y depends on the value of x. For the inverse, it should be the other way around. So y becomes the independent variable, x becomes the dependent variable. So we want to find a function that makes x depends on y in this case. How to do that? So we have the function here. We multiply both sides by +2. And then we subtract both sides by -2. Then we have x equals to 2y minus 2. Well, in some sense, this is already the inverse of y equals to half of x plus 1. But in the question, we are asked to express the inverse as a function of x. So in this case, after we get this inverse, we flip the position of x and y. So now we get y equals to 2x minus 2. So in this case, y equals to 2x minus 2 is the inverse of y equals to half of x plus 1. Any questions? Any question? Is it clear?
Still clear, sir. Yeah, still clear.
Clear, sir.
Clear. Okay. Now, the second example, we are asked to find the inverse of function y equals to x squared for x greater or equal to 0, expressed as a function of x. Now, my question is, why we can find the inverse of y equals to x squared if we restrict the domain to be non-negative numbers? Why? Anyone wants to help me? Anyone?
I'm sorry, sir. What's the question?
So here we have the function y equals to x squared. And we restrict the domain to be non-negative number. In this case, we may have an inverse. So why we can have an inverse for this case?
I don't know, sir.
Remember from the morning session that if we don't restrict the domain of x can be from -infinity to infinity, right? If we don't restrict the domain can be -infinity to infinity for this function. Am I right?
Yes, sir. Yes.
Yes. Okay. In that case, y equals to x squared is a one-to-one function or not?
No.
No, because For example, if we take x equals to -1 and x equals to 1, we will have the same value of y, correct?
Yep.
Yeah. Now, if we restrict the domain to be non-negative numbers, so x greater or equal to 0, then do we have a one-to-one function now in this case? So for y equals to x squared, and we restrict the domain of x to be x greater or equal to 0. Now, in this case, do we have a one-to-one function or not? Do we have a one-to-one function or not?
Yes.
Yes. Because we have a one-to-one function in this case, because we restrict the domain of x to be non-negative numbers, or x greater or equal to 0, in this case, we have a one-to-one function. That's why we can have the inverse of this function. So only to find the inverse of a function, we need to make sure that the function is one-to-one first. So if the function is not one-to-one, we cannot have an inverse in that case. Okay, understood?
Understood.
Okay, so for step 2 and step 3 is similar to this. So basically, we want to solve for x in terms of y. We get x equals to square root of y. Now we just interchange x and y. We have y equals to square root of x as the inverse of y equals to x squared for x greater or equal to 0. Okay, any question up to this point? Any question? Any question? No? Okay. Now we go to logarithmic functions. So what is a logarithmic functions? Logarithmic function is basically the inverse of exponent function. So previously we already learned about the exponent. Now we learn about the logarithm. So logarithm is actually inverse of an exponential function. Suppose that we have an exponential function y equals to a power x with a greater than 0 and a is not equal to 1. The inverse of this function is the logarithmic function with base a, that is y equals to log a of x. So here a is the basis. So we have log a, mean that we have a logarithmic function with base a of x. Understood?
Yes, sir.
Okay. So now there are two special logarithms that those are logarithm with base e and base 10. Base e is the here is the Euler's number that we learned this morning, and the other base is base 10. These two logarithms are so important that people have defined their spatial notations, namely this. So if we have logarithms with base e, we can write it as ln x. So ln here ln. Ln means logarithm naturals, because e is Euler's number, and also e is called natural numbers. That's why sometimes we, or most of the time, we write log e as ln. Ln stands for logarithms natural, natural logarithms. And for the base 10, usually people don't write the base. So if you find log x, it means logarithm with base 10. Other than that, we have to put the base. We have to write the base. So other than base e and base 10, we have to write the base. For the logarithm function, we have some algebraic properties, especially this here for the natural logarithm. For any numbers b, for any positive numbers b and x, the natural logarithm satisfy these rules. First, product rule. So if we have ln b times x, we have ln b times x equals to ln b plus ln x. And also quotient rule. If we have ln b over x, we have ln b minus ln x. And reciprocal rule, if we have ln 1 over x, it is equal to minus ln x. And the last one is the power rule. If we have ln x power r, we can move the power in the front. So now it becomes r times ln x. I'm quite sure that you already learned these rules in your high school. So let's go to the example. First example is we have ln 4 plus ln sin x. Since the base are the same, all natural logarithms, then we can combine them to be like this, ln 4 times sin x. And the second example is we have quotient rule. So in this case, we have ln numerator minus ln the denominator. And the third example is from this reciprocal rule and the power rule. We have ln 1 over 8 equals minus 3 ln 2. Up to this point, any question?
Yes, I have, sir.
Yes?
Can you back to the slide? I mean, sir, I want to ask the theorem say that for any numbers that b greater than 0. How about the rules number 2 and number 3? Kalau dia yang rule number 2-nya itu, sir, kan itu quotient rule kan. Kalau yang nomor 3 itu kan reciprocal rule itu.
Yes.
Nah, kalau itu kan di aturannya dibilangnya b greater than 0, than 0. Berarti b lebih besar dari 0 kan, sir? Nah, bagaimana kalau nomor 2-nya itu gimana ya bilangnya? Jadi
b is negative and x is negative, you mean?
No, I mean, how about if the b is 1? How about the b if it's 1? Jadi kan kalau nomor 2, nomor 3 itu kan, sir, bedanya cuma yang nomor 2 itu kan b per x. Kalau nomor 3 itu kan 1 per x. Nah, bagaimana kalau nanti seandainya ln 1 per x?
Okay, I understand. So basically the rule for number 3 is obtained from the number 2 because, ln, you mean, let me write it like this. Ln 1 over x, we need to write it like ln 1 minus ln x, like this, right?
Yes, sir.
So what is the value of ln 1? So any logarithm with any base, so for any a greater than 1, for any a greater than 0 and a not equal to 1, we have log a of 1 equals to 0 because a power 0 equals to 1. So basically ln1 is equal to 0. Then we have 0 minus ln x. In this case, we have only minus ln x. Clear?
Oh, yeah. I see. Thank you, sir.
So for any logarithm, log of 1 is always 0. Good question. Some other important rules that you need to remember. First, the inverse property for a power x and log a of x. If the base is a, we have a power log a of x equals to x, and log a of a power x is also equals to x. If the base is e, we have e power ln x is x, and ln e power x is also x. And the next rule is that every exponential function, we can always write it as the power of the natural exponential function. Why? Because it is like this. A power x is equal to, so if we take a look at this, e power ln x is equal to x. So if we have a power x, then it is equal to e power ln a power x. And for this ln a power x, we can write a power a ln x like this. Oh, sorry. A power x ln a, yeah, like this. This is how we get the second rule. And then we can also change the base of a logarithmic function like this. So log a of x is equal to ln x over ln a. So we see here the denominator is ln x, and the numerator is ln x, and the denominator is ln of the base. The base is a here. You don't need to memorize them. Everything is in these slides. For example, here. So if we have a radioactive element, we can actually calculate the half-life of the radioactive element. And the half-life of a radioactive element is actually not does not depend on the initial volume of that radioactive element. So what is the half-life of a radioactive element? Is basically the time required for the radioactive nuclei in that radioactive element becomes half of its initial value. And the function is like this to calculate half-life, the decay of a radioactive element. Y equals to y0 e power minus kt. And here, if we want to calculate the half-life of the radioactive element, is simply we make y equals to half of y0. So we can strike out. We can cancel the y0 from both sides. Now we have only e power minus kt equals to half. And if we take ln of both sides, we have minus kt equals to ln half equals to minus ln 2. So from here, we have that t equals to ln 2 over k. In this case, we know that half-life of a radioactive element is basically ln 2 over k, only depends on k, does not depend on the initial value of that element. Is it clear? So from the second step, to the third step. Is it clear?
Sir, can you explain back the third step, please?
Okay. Now let me explain it completely. We have e power minus kt equals half. In this case, we can take ln of both sides. So ln of e power minus kt equals ln half. So we have both sides like this. And from here we have, so the power can be put up front. So we have minus kt ln e equals to ln half. And we know that ln e is equal to, what is ln e? So ln e is equal to e log e equals to, what is the value of log e with the base e? 1. Because e power 1 equals to e, right?
Okay.
Yeah. Right.
Ln e is equal to 1. So in this case, we have minus kt equals ln half. That's why from the second line, we can have the third line. Okay, is it clear?
Okay, clear, sir. Thank you.
Clear, sir.
Now the challenge. What is the simpler expression for a? E power ln 7.2. E power ln 7.2 equals to, remember this, e power ln x equals to x. So e power ln 7.2 equals to what here? Hello.
Yes, sir.
Yeah, e power ln 7.2 equals to what value here?
7 or
7.2. Correct. Now b. We have e power minus ln x squared. E power minus ln x squared. This is equal to e power ln x squared power minus 1. So we have x squared power minus 1. Here we have x power minus 2, or 1 over x squared. Agree?
agree, sir.
Okay.
Agree, sir. Agree.
Now the third one, e power ln x minus ln y. What do we have here? What is the final, the simplest form of this part of e power ln x minus ln y? Okay, then if no one wants to answer it, I will just tell you the final answer. This is x over y. You can try to compute it yourself at home. Trust me now that this is correct. Okay, anyone get the same result as me? Anyone here?
Sir.
Yeah.
I get 1 per y.
1 over y. Are you
Mhm.
sure?
Yes, but correct me if I'm wrong.
Okay. E power ln x minus ln y. If we take a look at the power, you can make it to be e power ln x over y, right?
Yes, sir.
That's why now we have x over y.
Oh, okay, I get it. I get it. Thank you, sir.
Okay. This one. Ln square root of e. 2 ln square root of e. In this case, this is equal to 2 ln e power half. Square root is something power half. Now we have 2 times half of ln e, and ln e is equal to 1, so we have 2 times half, which is 1. For the second one, we have ln of ln e power e. What is the final, the simplest result of the simplest form of this ln of ln e power e? Okay, try it by yourself. I believe that the simplest form is 1.
Why, sir?
Why? Okay, let's see. Ln of ln e power e, we can make it like this. Ln of e times ln e, right? And ln e is equal to 1, so that's why now we have only ln e. That's why it is equal to 1. Agreed?
I see, I see. Thank you, sir.
Now, ln of e power minus x squared minus y squared. It should be easy. This should be minus x squared minus y squared. Okay, because we simply need to move the power front and then multiply by ln e. Ln e is equal to 1. That's why we only have this. Now, this one. Solve for y in terms of t or x. So we have ln y equals to 2t plus 4. In this case, we want to make it, we want to find y as a function of t. So in this case, we make both sides exponent. So e power ln y equals e power 2t plus 4. For this step, any question? No? Is it
No.
clear?
Clear, crystal clear.
Okay, now we have e power ln y is equal to y. Now for the right side, we have e power 2t plus 4. So now we already have this form, which is the answer to this challenge. For this one, you can do it by yourself at home. Now we learn a little bit about inverse of trigonometric function, which I already mentioned earlier. In general, trigonometric functions do not have inverse, since they are not one-to-one for the whole numbers. However, if we restrict their domains, for example, y equals to sine of x, we restrict the domain to be only from minus pi over 2 up to pi over 2. We can have the inverse, and y equals to cosine of x. If we restrict the domain from only from 0 to pi, we have a one-to-one function. You can see it clearly in the graph. In this case, we can also have the inverse, and for the tangent of x, if we restrict the domain, sorry, this should be open interval, so this should not be square bracket. This should be just the normal bracket. So we do not include minus pi over 2 and pi over 2, but anyway, if the domain is restricted to minus pi over 2 up to pi over 2, the tangent of x can also have an inverse. What is their inverse? What are their inverse? The inverses. The inverse are like this. So the inverse of sine of x is arccosine of x, which is written like this, sine power minus 1. And the plot should look like this. Now we simply flip the domain and range. So here you see the range is from minus 1 to 1. In the inverse, that becomes the domain. And in sine x, the domain is from minus pi over 2 up to pi over 2. That becomes the range of the inverse. And also you can see for cosine of x and tangent of x, these are the inverse. For example, if we are asked to evaluate the value of sine inverse of square root of 3 over half, square root of 3 times half, so square root of 3 over 2. The inverse is pi over 3 because of what? Because sine of pi over 3 is equal to square root of 3 over 2, and pi over 3 is also in this domain. So we need to find the value of sine with where the angle is in this domain. And for the cosine, we restrict the domain to be from 0 to pi. That's why the answer of a cosine inverse must be within this domain. So any question up to this point? I'm not going into detail for the trigonometric function, but you can try all the questions here. Most of them are exponential and logarithmic. And there's one here, trigonometric function. Now we jump to the next material. So before that, any question? No?
For me, no, sir.
No.
Okay. Now, for the next 4 parts, we learn all about limits, which I think I can go much faster than before, because inverse is basically a little bit harder than limits. But I will go a little bit slow on part 3 and part 4, I think. So the first part is the limit of function. What is the limit of function values? So basically, if we have the function f of x equals x squared minus 1, over x minus 1, how does the function behave near x equals to 1? So we are not trying to find the value when x equals to 1. Why? Because if x is equal to 1, then the denominator here becomes 0. In that case, the function is not defined. But we just want to know what is the value of f of x when x is very, very close to 1. In that case, we are talking about limits. So when for any x not equal to 1, we can actually write the function like this. So we factorize the numerator into x plus 1 times x minus 1. So we can cancel the x minus 1. That's why for x not equal to 1, we have f of x equals to x plus 1. This is only for x not equal to 1. So in this case, we have that actually the graph of the graph of f is the line y equals to x plus 1. It is just a straight line with slope with the gradient to be equals to 1. And in this case, only the point where x equal to 1 is removed. So this line without the point 1, 2 is basically this function. So in this case, we have that even though f of 1 is not defined, we can make the value of f of x as close as we want to do by choosing x close enough to 1. So basically, we want to approximate the value of f of x at 1, but we are not exactly calculating the value at x equal to 1. So in this case, we are talking about limits. So basically, the rough definition of limit is like this. So suppose that we have f of x defined on an open interval about c. Here, c is the point. In this example, c is 1. So except possibly at c itself. So f is defined everywhere, but it is not necessarily defined at c. It can be defined at c, but it cannot. It can also not be defined at c. In this case, if f is arbitrarily close to the number L, so if f in this case f is very, very, very close to 2. So here in this example, L is equal to 2, as close to L as we like. Okay. For all x sufficiently close to c. So here for all x sufficiently close to 1. We say that f approaches the limit L as x approaches c. And we write the limit like this. And well, this is the rough definition of limit. And you don't need to learn about the formal definition of limits. What you need to remember is the way you compute limits in your high school. So, for example, we consider this function f of x like before, and we consider g of x like this, and h of x like this. We have that for f of x, if x is not equal to 1, if x is not equal to 1, the form of fx is actually equal to h of x. But for g of x, here we specify at x equal to 1, the value of g of x is 1, not 2. But for these cases, we have that the limit of x, f of x as x approaches 1 is equal to limit of g of x as x approaches 1. and also equal to limit of h of x as x approaches 1. That is equal to 2. Any question at this point? I hope that you still remember limits from your high school. Any question? No? If not, then yeah.
No, sir.
Oh, okay. And there are two special examples. So if we have identity function that is f of x equal to x, then for any value of c, we have that limit of x to c of fx is actually c. And if the function is a constant function, the limit always exists. That is limit f of x as x approaches c is equal to the constant value. So now this one, we have the graph of f of t. Can you tell me what is the value of limit f of t as t approaches -2? What is the value of the limit? Can you tell me? According to this graph, what is the value of the question A?
I'm sorry, sir. Pardon me.
Yeah. So according to the graph here, let's consider that these blue lines are the graph of f of t. So the first question is, what is limit of f of t as t approaches -2? What is the value of f of t here? T approaches -2, -2 is here. So limit of f of t is? Hello.
-2, sir.
No. No. Any other answer? So the t is the horizontal axis, right? So the t approaches 2 here. What is the value of ft? Sorry. What is the limit of ft at this point? The value is close to. So from the left, the plot raise up to here, up to t-axis, and from the right, it also increase up to t-axis. So f of t at t-axis is equal to what here? See, the f-axis is from -1, 0, 1. So at this point, this is -2, comma
0.
0. So in this case, what is limit of f of t as t goes to -2?
-2,0.
It is equal to 0.
Tuh kan 0.
Yeah, it is equal to 0. Why? Because okay, here the circle that is not filled. So the empty circle mean that the value of ft here at point t equals to -2 is not defined. So we don't have the value of f of t, but we can compute, we can evaluate the limit, because from the left, from this side, from the left, it is going to 0, and from the right, it is also going to 0. That's why the limit is going to 0. Okay. What about the second one? Limit f of t as t goes to -1. What is limit f of t as t goes to -1? t equals to -1 is where? This one, this one, this one, or this one?
I still don't understand, sir.
Okay. This is the graph of f of t. Okay. So basically, f of t looks like this before t equals to before t. So when t less than -2, the graph is straight line that increase from somewhere to 0. But 0 is not included. And from -2 to -1, f of t decrease in a straight line manner. But so from 0 to -1, but 0 is not included. And for t from -1 to 0, the value of f of t is a constant number, like this, is a straight line. But -1 is not included. Sorry, -1, 0, -1 is not included. And at t equals to 0, the value of f of t is 0. And at t at the positive t, the value is equal to 1. So the blue lines is the graph of f of t. For a, limit f of t as t goes to -2. So from the left side, f of t goes to 0. From the right side, f of t also goes to 0. That's why the limit f of t as t goes to -2 is equal to 0. Up to this point, is it clear? Hello. Is it clear? Okay, let me remind you
watch
that.
this again.
Yeah.
Yeah, it's okay, sir. Just continue. I will watch this video again at record.
Okay. Let me remind you that we don't care how f of t is defined. Like, for example, here we have the precise definition of f of x. Here we have the precise definition of g of x. Here we have the precise definition of h of x. But in this example, we don't care what the f of t, what is the definition of f of t. We just know that the graph looks like this. We just know that the graph looks like this. So in this case, let me draw it here with my poor drawing. Or okay, snip. Let me add it here. Insert. Oh, I can actually screen clip. Insert, just screen clip. Okay, now we have this picture. We draw on top of this. So the first question is limit t goes to -2 f of t. Here the horizontal axis is t and the vertical axis is f of t. So we have as t goes to 2, so from the left, here t goes to 2 from left. And here we have, okay, let me draw it with different color. T goes to 2 from right. Okay, up to this point, is it clear?
Clear, sir.
Clear. Now, the concept of limit is basically, okay, we want to make t as close as possible to -2. Sorry, this is not 2, but -2. We want to make t as close as possible to -2. But what we want is to find the value of f of t when t goes as close as possible to -2. So we see here, when t goes to -2 from the left, f of t goes to when t goes to -2 from the left, f of t goes to, so it increases, the value increases this until when it is very, very, very close to -2. So when t very, very close to -2, what is the value of f of t? Here is 0, okay? When t goes very, very, very close to -2, from the left, what is the value of f of t? So let's say we want to find the value of f of t that is at this point, at this small green dots. What is the value of f of t at that point?
Zero.
Yeah. It is not equal to 0, but is very close to 0, right? Okay.
Okay.
Is it clear for this part? Now,
Clear.
when t goes to -2 from the right, f of t goes to, so here, from the right, the value of f of t goes to what value? Hello.
Close to 0 also.
Yeah, it is also goes to 0. That's why, in this case, since for both cases, so from the left it is going to 0, from the right it also goes to 0, then in this case, limit f of t as t goes to -2 is equal to 0. Is it clear? Is it clear?
Yes, sir.
Now, the second question, what is the value of limit of f of t as t goes to -1? We can clearly see from the graph actually. What is the value of the limit? As t goes to -1?
-1 bukan, sir?
Yeah, -1, correct. Because it from the left, it is a straight line down, slanted. so a little bit slanted, so it goes decrease up to -1 at this point, and also from the right it goes to -1, and it just so happens that at the same point the value of f of -1 is also -1. So in this case, B is quite clear. How about C? T goes to 0. What is the limit? T goes to 0. What is the value of this limit? Answer. Wrong answer is also an answer. Come on.
0 bukan, sir.
0. Okay, one answer. The other answer?
1 maybe, sir.
1. Any other answer?
-1.
Yeah, because the value of the limit can be -1 or can be 1 here, because when we approach from the left, it is equal to the value of the limit of ft goes to -1, right? When we go from the right here, up here, the value of the limit goes to 1. In this case, the limit does not exist. So we cannot compute the limit in this case. Understood?
Yes, sir.
So basically, because from the left and from the right, we reach the different value, that's why the limit does not exist. How about the last one? Limit as t goes to -half.
Also not exist.
Yeah,
Not exist also.
why?
Because
my-
there's no 0.5.
Oh, okay. Where is t equals half? Where with is here, right? Here is -0.5, right? So if we take a dashed line here, we want to find limit f of t at this point. So the question is, what is limit f of t as t goes to -0.5? In this case, it is equals to -1. Do you know why? Anyone knows why?
I don't know, sir.
No? Okay. So t -half is here, right? So now let me take a different color. Maybe purple. Okay. So we want t goes to half from the left and goes to -half. Sorry, t goes to -half from the left and also from the right. So f of t from the left goes to f of t here from the left. It goes to
-1.
-1, and from the right it goes to
-1.
also
-1.
-1. That's why the limit when t goes to -half of ft is -1. Is it clear now?
Yes, sir.
Okay. Now the next, can you explain to me why the following limits does not exist?
Karena penjemputnya 0.
Yeah, because since we are computing limits, our approach should be a little bit different. So limit x goes to 1 of 1 over x minus 1. Okay, let's take a look at a value where x equals 0.999. What is the value of 1 over x minus 1? It becomes 1 over 999 over 1000 minus 1. That is equals to 1 over minus 1 over 1000. That is equals to minus 1000. Now we make it closer to 1 from the left. Okay, x equals to 0.9999. 1 over x minus 1 equals to equals to 99999 over 100,000 minus 1, which is equals to minus 100,000. And if we make it very close to 1 from the left, so x is 0.999, I don't know how many nines, it will become something like this, minus something that is very big. So as x goes to 1 from the left, 1 over x minus 1 goes to minus infinity. Is it clear for this one?
Yes, sir.
Yeah, because when we choose x very close to 1, but from the left, the denominator is somewhat some value that is negative, but very close to 0. That's why the 1 over something negative that is very close to 0 is negative infinity. Now we try to approach it from the right. X equals 1.001. Then we have 1 over x minus 1 is equal to 1 over 1,000,001 minus 1, which is 1 over 0.001, which is 1,000 positive. And then we make it closer again, 1.00001, then 1 over x minus 1 equals to 1 over 1.00001 minus 1. That is 100,000. So if we choose x very close to 1 from the right, we have 1, let's say 1,00. I don't know how many zeros here. Then it will become something like don't know how many zeros. Something very big that is positive. So now x goes to 1, if x goes to 1 from the right, then 1 over x minus 1 goes to
Infinite.
Positive infinity.
Yeah. Since from the left, if we approach it from the left, it goes to minus infinity. If we approach it from the right, it goes to positive infinity. That's why the limits does not exist. Understood? Is it clear?
Yes, sir.
Yes, sir.
Okay. Now the limit law. So there are some laws of limits that you need to know. If say we have a limit of f of x as x goes to c is equal to L, and limit of g of x as x goes to c is equal to m. Then we have these 7 rules that you don't really need to remember, as long as you know that I already wrote it in the slides. You can always read the slides. Now let's just go to the example. So we have previously that limit of a constant number is also a constant number. So limit of constant number k is equal to k. Limit of identity here x as x goes to c is equal to c. And also we have these rules for limits. So the first limit of x power 3 plus x 4x squared minus 3 as x goes to c is simply like this. So we have we separate the limit because we have the sum rule like this one. So we can separate the limits like this. So now we have limit of x power 3, limit of 4x power 2, and also minus limit of 3. That's why we get c cubed plus 4c squared minus 3. The same thing happened with the fraction, the second limit. Since we have this quotient rule, as long as we can guarantee that the denominator is not equal to 0, we can do the same thing. So we can put the limit in the numerator and also in the denominator. Here we can see that the denominator, since it is x squared plus 5, it can never be 0. So whatever your value of x is, the value is never 0. So we can apply this quotient rule. And then for each limit, we do the same thing as a, so we get this result. As for the c is from the root rule number 7. So basically, we can, if we have a limit like this, we can put the limit inside the square root now, like this. And then we apply the same thing as we did in a. So we get something like this. So for this example, any question?
Yeah, still clear.
So clear?
Yeah.
Okay. Now, so from here, actually, we see that if we have a polynomial, the limit is straightforward like this. So that's why if we have a polynomial of order n, then the limit is also straightforward like this. If we have a rational function like this, like the second example, we also have the same thing. We just need to put c, substitute x to c, so that we get this expression. As long as we know that q of c is not equal to 0. Example is this one. So So we are asked to compute this limit. So limit of x cubed plus 4x squared minus 3 over x squared plus 5 when x goes to minus 1. So we simply substitute x with minus 1. Why? Because if we put minus 1 to x squared plus 5, the value is not 0. That's why we can directly compute it like this. The solution is quite easy in this case. For this example, is it clear?
Yes, sir.
Now, what is the value of this limit? What is the value of this limit?
Negative 40.
Negative 4. Yeah, that is correct because we simply substitute minus 3 to x squared because here we have a polynomial. So it is easy. We just need to substitute minus 3 to x squared. Then we have 9 minus 13 is actually minus 4. So that is the correct answer. Any question?
No, sir.
No? Now, the next part is how we eliminate common factors from zero denominators. So as you remember, for a function, we cannot have 0 as the denominator. That's why we need some tricks in computing limits for a fraction that has a 0 denominator. For example, here limit of x squared plus x minus 2 over x squared minus x as x goes to 1. In this case, we see that if we substitute 1 to x squared minus x, we have 1 minus 1 equal to 0. In this case, we cannot directly substitute x equal to 1 because it makes the denominator 0. But turns out that x equals to 1 is also a factor of the numerator, because if we substitute 1 to the numerator, we have 1 plus 1, 2, minus 2, 0. And we have to remember that basically, when we want to evaluate a limit, we are not evaluating the function at that exact point, but we evaluate the function at a point very, very close to that point. So that's why only in limit we can do this cancellation. So only when computing limits, say we have this and then we factorize both numerator and denominator, we have this expression now, and only in limit we can cancel the term that makes the function to be 0. That's why here we can cancel x minus 1. So we are left off with x plus 2 over x. And we can, after this part, we can substitute x equal to 1 to x plus 2 over x. And we have 1 plus 2 over 1, which is equal to 3. Any question?
No, sir.
No. Now, the next example is we are asked to evaluate this. In this case, we know that the denominator is equal to 0 because, if we substitute 0 to the denominators, we have that the denominators equal to 0. And in this case, actually, we have different tricks. In this case, as you see, the one thing above, if we put 0, we also have 0 as the numerator. But for this case, we try to multiply the numerator by something else, like this, x squared plus 100 times, plus 10 over square root of x squared plus 100 plus 10. Why? Because of this concept. Basically, if we have a plus b times a minus b, it is equals to a minus b times a plus b, which is equal to a squared minus b squared. I hope that you still remember this special multiplication from your high school. And that is the reason why we try to do this. We try to multiply the numerator now by something that when we substitute 0 is not equal to 0. So let's say if we substitute 0 to x squared plus 100 is 100. We take the square root of 100 is 10, plus 10 is 20, not 0. So, but on the other hand, in this part, this is negative. So if we put 0 to x squared, we have that 10 minus 10. This part is 0. Now, in this case, we try to multiply it by this. And just take note that usually, when we have this kind of form, which contains a square root, usually we do this kind of trick. Why we can do this? Because the numerator and the denominators are the same, and which means that we actually multiply this guy. We multiply this guy by 1, so we are not changing anything. But turns out that after we do the multiplication, we have that the numerator now becomes only x squared, and the denominator becomes x squared times square root of x squared plus 100 plus 10. Now, in this case, we can cancel the x squared term. After that, we can substitute x equal to 0, and we have 1 over 20. For this example, any question? Any question?
No, sir.
Okay. Now, let's try to evaluate this. Limit x goes to 5, x minus 5 over x squared minus 25. In this case, can we directly substitute 5 x equal to 5? Can we do that or not?
No.
No. Okay. In this case, for this example, we simply need to factorize them. X goes to 5. The top one is already the simplest form, this, and the bottom one, the denominator, can become x plus 5 times x minus 5. Understood? Is it correct?
Correct, sir.
Correct.
Yes,
Now
sir.
we can cancel the x minus 5, and we have limit of x goes to 5 equals 1 over x plus 5, which is 1 over 5 plus 5, which is 1 over 10. Is it clear?
Yes, sir.
Yes. Clear, sir.
Now, I'm going to talk about the sandwich theorem. Why the theorem is called sandwich theorem? Because we are talking about a function f of x that is placed in between g of x and h of x for all x. So it looks like f of x is sandwiched between g and h in some interval. So suppose that we know limit of g of x as x goes to c is equal to limit of h of x as x goes to c equals to L. Then in this case, we can conclude that limit of f of x, no matter what f of x is, as x goes to c is also equals to L. That is basically what the sandwich theorem says. For example, here. Suppose that we have the function u of x is squeezed between 1 minus x squared over 4 and 1 plus x squared over 2 for all x not 0. What is the value of u of x as x goes to 0? So in this case, we don't care about the function u of x, but we know that u of x is squeezed between 1 minus x squared plus 4 and 1 plus x squared over 2. Then in this case, we can compute the limit of the left side as x goes to 0, which is 1, and the right side as x goes to 0, which is also 1. In this case, no matter what u of x is, the sandwich theorem says that limit of u of x as x goes to 0 is also equals to 1. Any question?
No, sir.
I hope that you understand. Okay. This is basically what the sandwich theorem says. So if u of x is very, very, very complicated, but we know that u of x is squeezed between between two functions for all x, then we can always calculate the limit of u of x. Is what the sandwich theorem says, because well, the name sandwich means that we squeezed the function between two other functions. Now let's try to evaluate this. What is the limit of limit x goes to 0 to sine x minus 1? It should be easy. Well, for this case, we don't need the sandwich theorem actually. We just need to substitute 0 to x. So we have 2 sine 0 minus 1, which is 2 times 0 minus 1, which is 0 minus 1, which is minus 1. Is it clear?
Clear, sir.
Okay. There are some challenges that, well, 9 that you can do at home in your free time. Now we go to one-sided limits, which I actually have mentioned briefly before. So the previous limit that we studied, okay, let's take a look at this graph. So this is the graph of y equals to x over absolute value of x. In this case, the limit of y when x goes to 0 does not exist. Why? Because when we go from the left, the value is -1. When we go from the right, the value is 1. That's why in this case, we don't have the limit at x equal to 0. But we do have the limit when we only approach 0 from the left, which is -1. And also when we only approach 0 from the right, the limit is 1. In this case, okay, the previously learned normal limits are actually called two-sided limits because we need to approach it from two sides. But we can still approach the value of function f from one side. That is called the one-sided limit. Basically, for one-sided limit, we have a right-hand limit and left-hand limits. For the right-hand limits, the notation is like this. This means that we approach x to c from the right. From the right, okay. From the right is denoted by plus. And from the left is by negative. For example, if we have this guy, so we have a picture of a half circle like this. This is -2. This is 2. And this is the plot of f of x equals to square root of 4 minus x squared. Here is the horizontal axis is x. The vertical axis is y. Now, the limit of x goes to 2 from the left. Since we only define the function on this interval from -2 to 2, then we can only have at point 2, we can only have a left-hand limit, which is we approach 2 from the left. So in this case, limit x goes to 2 from the left of fx is equal to 0. But limit of x goes to 2 from the right of fx does not exist. And also limit x goes to 2 of fx also does not exist. Why? Because we only have the limit from the left, but we don't have the limit from the right. That's why limit the normal limit also does not exist. Is it clear?
Yes, sir.
Any question? No? Okay. Now, so basically we say that the limit exists here. Limit exists as x goes to c if and only if the limit from the left and the limit from the right are equal. But if the limit from the left and the limit from the right are not equal, then the limit does not exist. So this is basically what the definition of our previous limit, our normal limit. And let's take a look at this example. So at x equals to 0, here is the graph. we have that x goes to 0 from the right. So 0 from the right. So from 1 goes down to 0. The limit goes to 1. But as x goes to 0 from the left, the limit does not exist. That's why the limit at x goes to 0 also does not exist. Why? Because the function is not defined on the left of x equal to 0 here. Is it clear?
I'm sorry, sir.
Yeah.
Can you move to the before slide? Yeah. I want to ask, sir, what is L mean? What does the L mean?
Here it's just suppose that the value of the limit is L. So L can be any constant. Basically, L is the value of the limit. So let's say limit f of x as x goes to c from the left is equal to x, and limit f of x as x goes to c from the right is also equal to x. Then we have limit f of x as x goes to c equals to L. For this example, from the left, the limit goes to -1. From the right, limit goes to 1. We can consider here L is equal to -1, but on the other side, L is +1. The two L's are different. That's why we don't have the limit. It's simply like that. Is it clear? Okay, let's see from this example. Okay, for this example, we have that limit of x squared plus x minus 2 over x squared minus x as x goes to 1 is equal to 3. In this case, L is 3. So it's just L can be any number as long as it is the limit value of the limits. Is it clear?
Yes, sir.
Yes, sir.
Okay, now at x, now we back to this example. So at x equal to 1, we have that limit of f of x as x goes to 1 from the left is 0, because it goes down, and then the value that is at x very close to 1, the value of fx is 0, or is very, very, very close to 0. Even though we know that in this case, f of 1 is actually 1, because we see here at x equal to 1, at this point, we have a blank circle, and at f1, at y equals to 1, we have a full circle. That's why it means that the value of f at x equal to 1 is actually 1, not 0, but the value of the limit from the left is 0. Is it clear?
Yes, sir.
Okay, now the limit of f of x as x goes to 1 from the right. Okay, from the right is actually equals to 1, because if we approach this point from the right, we approach 1 from the right, the value of f of x approaching 1. That's why limit f of x as x goes to 1 from the right is equal to 1. So in this case, since from the left and from the right, the limits are different, that's why the limit does not exist. So the normal limit does not exist, because the right hand and left hand limits are not equal. Is it clear?
Yes, sir.
Now, at x equal to 2, the limit of x goes to 2 from the right, the limit goes to 1, even though the value of f of 2 is actually 2. And if we approach it from the left, is also equals to 1. So in that case, the value of the limit as x goes to 2 is equal to 1. Even though here we have that f of 2 is actually 2. Is it clear? Any question?
Nope.
Yeah. Okay. Now, the last part of this example is, okay, we try to approach 3 from the right and from the left. They are actually the same. So from the left is the limit is 2. From the right, the limit is also 2. That's why this limit as x goes to 3 is actually 2. And it just it also happened that f of 3 is equal to 2, because here we have a full circle, a filled circle. And at x equal to 4, the left hand limit is 1. The left hand limit is 1 because when we approach from the left, the value of f of x is going to 1, even though f of 4 is not equal to 1. Actually, it is somewhere here at this point. And limit from the right does not exist because the function is not defined on the right of x equal to 4. So that's why this limit is also not also does not exist. Now, here's the challenge. A, is it correct or not? For this picture, for this graph, A is correct or not? Limit of f of x as x goes to -1 from the right equal to 1. Is it correct?
I don't know, sir. Maybe correct.
Okay. X goes to -1. -1 is here, right? X goes to -1 from the right. So we have here from the right. And the function is going up to this point, which is 1. So now we can check whether limit f of x when x goes to -1 from the right, whether it is equal to 1 or something else. So here it is equal to 1. Is it correct or not? Just answer it.
Correct, sir, I think.
Yes, correct. It is correct. Why? Because when we go to the left, so from the right to the left, so we want to approach -1 from the right. So from the right side of -1 is here, right? Is where the hand is, where my cursor is. We approach -1 from the right, so we go slowly from the right to -1. And here we see that the value of f of x goes to 1. That's why limit of x goes to -1 from the right is 1. Okay, B, f of x, the limit of f of x as x goes to 0 from the left is equal to 0. Is it correct or not? Is it correct or not? So x goes to 0 from the left. So let's say -1 is in the left of 0. So we go from -1 to 0 slowly. So we want to approach 0 from the left. So goes to the right slowly. And we see that the value of f of x goes to 0 in this case. So B is correct or not?
Not.
Why? So B is actually correct. Even though we have that f of 0 is 1. So here at x equal to 0, f of x is 1. Because here we have a blank circle and the filled circle is up there. So we have that f of 0 is 1. But when we compute the limit of f of x at 0, and we approach it from the left side, it is going to 0. So B is correct, actually. Okay, C, is it correct or not? Oh, yeah. C, is it correct or not? Of course, it is not correct, right?
Not correct.
Of course, it is not correct because we have that B is correct, and of course, C is not correct. Okay, what about D? Is the limit x goes to 0 from the right and from the left are the same? Are they the same or not?
No, not.
No? Okay. From the left, we know that the limit is, so from the left, we know that the limit is 0. But from the right, what is the limit? Remember my illustration in this picture? We try to approach with these arrows. So now from the left, we approach 0 from the left. So we go from -1 to 0 slowly. Go to the right slowly, slowly, and we get that the value of f of x goes down slowly to 0. That's why the limit of f of x as x goes to 0 from the left is equal to 0. How about from the right? From the right, we go from 1 to 0 slowly. Go slowly to 0, and we get that the value of f of x goes down slowly to also 0 from the right. In this case, the answer for D, is it correct or not?
Correct, sir.
Yes, correct. This is correct. So since the limit from the right and from the left are the same, the question is whether this exists or not. So limit of x goes to 0 of f of x, is it exist or not? So the statement is limit x goes to 0 of f of x exists. Is it correct? Is it correct?
Not, sir.
Why not? Yeah. As long as the left hand limit and the right hand limit are the same, then the limit exists. This is basically what this theorem says. So in this case, the answer for E, is it correct or is it not correct?
Correct.
Yeah, this is correct. Okay, what about F? Is it correct or not?
Not me.
Yeah?
Not, sir.
No? Okay. What is the value of the limit as x goes to 0 from the left?
0.
0. And what is the value of the limit as x goes to 0 from the right?
0. Oh,
0. Then is it correct or not?
correct.
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 Correct, sir.
Now G, is it correct or not?
No, it's not.
Of course not. Yeah. Okay, now H, is it correct or not?
Correct.
Correct.
X goes to 1, it should work from both sides. So it should work from the left and from the right. X
No.
goes to 1. Okay, so this is correct or not?
Nope.
No, why? Why not correct? Who was that?
Me.
Okay. Jason, why not correct?
Wait. Because the left and the right side must be equal, right?
Yeah. So from the left, what is the value?
Wait. The left one is, the value of the left one is 1. Minus
from
1,
the right?
and from the right is between 0 to 1.
From the
Correct me
right
if
is
I'm wrong.
actually 0. Here, from the right is 0. It's not between 0 or 1. Because you see this line, we go to 1 from the right, meaning that we try to go from 2 to 1 slowly. What is the value of f? It is 0, right?
Yes, sir.
Yeah, so from the left, we have that limit is 1, but from the right, limit is 0. So H is wrong. Now I, is it correct or wrong?
Correct.
Are you sure? This, there is no plus or minus, so it should work both ways. It should work from the left and from the right. So I is correct or not? X still goes to 1. We know that from the left, the limit is 1. From the right, the limit is 0. So I is correct or wrong?
Wrong.
Wrong. Yeah. So I is not correct. Why? Because the limit at x goes to 1 is, the limit does not exist, because from the left and from the right, they are not the same. Okay, understood?
Yes, sir.
Okay, J, is it correct or not? Is it correct or not? J. It goes to 2 from the left. Goes to 2 from the left. So we go from 1 to 2 slowly, and we see that the value of f of x goes to what number?
2.
Goes to f of x is the vertical axis, right? So f of x goes to, when x goes to 2 from the left, f of x goes to the vertical axis. We see here, this is 1, this is 0, so f of x goes to
1.
0. 1 is up here. 1 is up here. So if the point, so 1 is here, 1 is here. Down here is 0. Okay, so J is wrong or right?
Wrong, sir.
Wrong. Okay. Why? Because if we approach 2 from the left, the value of f of x is actually 0. So that's why the limit here is wrong. Okay, limit of x goes to -1 from the left does not exist. Is it correct or is it wrong? Is it true or false? From the left, is the function defined? To
Correct.
the left of -1, is it defined or not?
Define.
To the okay. This is my final drawing. This is my final materials for today because I have took your time like about 17 minutes. Sorry for that. Insert screen clipping. Now we click this. Let me move it here. I can so that I can draw. Okay, so here the function only defined from -1 to 2, right? So this side, the red side, is the left of x equals to -1, and the green side is the right of x equals to 2. Is it clear?
Clear, sir.
Clear. Now, here k. Okay, we start. We return to j. We use the. Let's use the purple color. Limit x goes to 2 from the left. Limit x goes to 2 from the left. F of x equals to something, okay? So we want to approach to here x goes to 2 from the left is something like this. So it is x goes to 2 from the left. So the arrow is like this. From 1 to 2. That's why we have x goes to 2 from the left. Now, what is the value of f of x here? Here, f, let me use different color. Here, f of 2 is actually equals to
0.
yes, is equal to 0. And it just so happened that also when we try to reach 2 from the left, the value of f of x is going to also 0, right? Because here in this point, f of let's say 1 point something is 0, and as we are going close to 2, the value f of 1 point something is also 0, and at this point that is very close to 2, f of 1 point, let's say 99999, and so on is also equal to 0. That's why limit of f of x as x goes to 2 from the left is 0. Is it clear?
Clear, sir.
Now, statement in K is limit of f of x as x goes to -1 from the left does not exist. Well, it is true because why? Because the function f of x on the left of my x equals to -1 is not defined. So we don't have anything here in the red area. That's why the limit does not exist if we try to approach it from the left. So it is correct. Up to this point, is it clear?
Clear, sir.
Clear. Okay, now the last one. Limit x goes to 2 from the right of f of x is equal to 0. Is it correct or not?
It's correct.
Goes to 2 from the right. Goes to 2 from the right. So
Not,
from
sir.
Mhm.
L is correct or not? Correct or not?
Correct, sir.
Well, I think I heard somebody tells me that this is not correct. Well, that answer is true. So L is not correct. Why? Because in the green area, which is on the right side of x equal to 2, the function is not defined. That's why we cannot have any limits here. So the limit should not be exist. So L is not correct. Understood?
Understood, sir.
Okay, then let me stop here. Next Friday, we will start from this challenge 2. It's okay if we are going a little bit slower than what it's supposed to be, as long as you understand what we are learning. Okay, before I end this session, any question?
I think not, sir.
No? Okay. Please make sure to learn the materials that I have uploaded in Microsoft Teams before next Friday so that we can go through the limits a little bit faster. Let me end this meeting today. See you next Friday. Happy weekend. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Good
Sir.
afternoon.
Waalaikumsalam. Thank you, sir.
Thank you.